And this next set of questions are sort of geometry questions. Throughout AP Calculus, we're going to deal with volumes and areas and perimeters and different geometric things. So this set of problems is in no way comprehensive of every geometry thing you need to know. Here we have a cone and a sphere and a kite. Where there's going to be other shapes that come up. So this is really just an idea of, okay, do you remember your volume stuff? What do you know the basic ideas? Do you know the basic formulas there? Because those will come up. Okay, so for this first one in particular, a right circular cone. Sometimes we get thrown off when we see that terminology, a right circular cone. That just means a regular cone. The base is a circle, and the vertex here at the top is directly above. It forms a right angle to the center of the base. You could have an oblique cone where it's slanted off to the side, or you could have a different shape, an ellipse for the base. It doesn't have to be a right circular cone. But typically when we just say cone, we think about a right circular cone. So with a right circular cone in particular, and some other cones as well, as long as the base is a circle, really. The formula for the volume is pi r squared, the area of the base, times the height, and then divide that by 3. Remember that the numerator here is just the formula for the volume of a cylinder, and if you take the volume of a cylinder and then you have a cone with the same base radius and the same height, the volume of that cone will always be exactly 1/3 of the volume of the cylinder. So that's the idea here. If you prefer to write this as 1/3 times this, of course that's the same. Whether you multiply by 1/3 or divide by 3, you're going to get the same thing. Plug in the given radius of 5, the given height of 8, multiply that out, simplify a little bit, and I believe you will get 200 pi over 3. Always better to leave that as 200 pi over 3 rather than to turn that into a decimal. We always prefer that exact answer if we can do it. Okay, 26, the ratio of the radius of sphere A to the radius of sphere B is 2:3. What is the ratio of the surface area of the two spheres? So there's two ways we can do this, and we'll do it the long way first. The long way would be to say, okay, well, what is the formula for the surface area of a sphere? So I'm going to say S is equal to, and it's 4 pi r squared. So we could just do this for A. We want the ratio of A to B. So A is going to be A over B is going to be 4 pi times whatever the radius of A is squared over whatever the radius of B is squared. Now, sometimes, so we're just saying, okay, let's just take the volume of, or sorry, not the volume, but the surface area of A and the surface area of B and find that ratio and simplify it. Now, a couple things to notice here. One, they didn't actually tell me what the radius of sphere A is and what the radius of sphere B is. They gave me the ratio of them. It's 2:3. Well, that means it could be 2 and 3, but it also could be 4 and 6. It could be 200 and 300. We don't know. But it doesn't actually matter, because when we're looking at the ratio, as long as it simplifies to this, when we plug it in here, it'll give us the same ratio. So I'm going to plug that in as 2 and 3 because that's the simplest two numbers I could plug in there. I could plug in 4 and 6. I could plug in 200 and 300. Anything that simplifies to a ratio of 2 and 3 will give you the same answer. And you can try that out, you know, if you're unsure. You plug in 200 and 300 and see that it will be the same. But notice here, everything except those those radii cancels out when we make the ratio. So it's going to be 2 squared over 3 squared, which is 4 over 9. And so that's our surface area ratio. And the same thing is going to happen with the volume, regardless of what the volume formula is, which, since we're reviewing, we'll write it down. The volume formula is 4/3 pi r cubed. But when I make the ratio of the volume of A to the volume of B, the 4/3 and the pi's are going to cancel out, and you're just going to get that ratio of the two radii cubed. So our ratio of A over B, in this case, is going to be 2 cubed over 3 cubed, which is 8 over 27. And I said we can kind of do this a long way or a short way. This, where you actually write out the formula and you think about it and you show the simplification, that would be the long way. The short way is simply remembering that you have that relationship where if you know the ratio of the side lengths of any two figures, and they are similar, then the ratio of the areas is going to be the ratio of the side lengths squared. And the ratio of the volumes is going to be the ratio of the side lengths cubed. That's something that you might remember. Hopefully that's something that makes sense. But again, if not, you can always come back and do it the long way and just figure out what those ratios are. Okay. Number 27. They give us this quadrilateral. They say that it's a kite, and they want to know the area of it. The area of a kite is not a formula that most of us have memorized. So the way that we're anticipating you're going to think about this is by adding up some of the smaller areas. And you could do it several different ways. You could find the area of each individual triangle and add those up. You could split it into two triangles, a top and a bottom. You could split it into a triangle on the left and a triangle on the right. Because in any of those cases, you have the base and the height of all of these triangles. No matter which triangles you choose, you have the base and the height. You also have the hypotenuse, which doesn't really matter. And you could figure it out if you needed to from the base and the height, but we don't need to. A sort of sneaky way to think about this is to recognize that if I just took this triangle on the bottom here and dropped it up here, well, that would actually complete the rectangle. And same on the other side. So then what I really have here is a rectangle with a total base of 21 and a height of 8. So then if I multiply that out, just do the 21 times the 8, you should get 168. That one there. So there's different ways to see it, different ways to look at it. But that's just kind of one way that I think is nice. Next one, two candles, right rectangular prisms. Again, what does it mean that it's a right rectangular prism? Just all the angles are right angles. So similar to the cone one, just what you would normally think about when you think about a rectangular prism. They give us all three dimensions of the first one, 15 by 8 by 8, and the second one is 5 centimeters higher, but the same length and width. How much additional wax? Two ways to do this. One is to find the volume of each and then subtract, but we can actually just think about that extra chunk. Let's see how my drawing goes here with my stylus. So the extra chunk is 5 centimeters higher. So far, not too bad. And that's pretty good. I'm proud of myself there. The extra chunk is 5 centimeters taller, and then it still has the same length of 8 and width of 8. So that's the extra chunk. I don't care about the first 15 centimeters of height at all. So I'm going to get, multiply that all together, 5 times 8 times 8, and I think I'm going to get 320 if I did my multiplication correctly there. Okay. So just a couple geometry problems there. Again, this is not a comprehensive review of every geometry thing that's going to come up ever. Just kind of reviewing some of the ideas, get our brain thinking about that. And most of the time, if not all the time, if something comes up from geometry and you're like, hey, I know what I'm supposed to do, but I'm just forgetting this formula, usually you'll be able to ask me or you'll be able to look it up. And it's not... I can't think of any time off the top of my head where there's like a really tricky formula on a test or a quiz, one that we don't use a lot. So I think you should be fine. All right.